Welcome to this edition of Weekly Dialogues. This is going to be an unusual Weekly Dialogues. I have with me Jonathan Crabtree from Australia, all the way from Australia. And welcome, Jonathan. And he is a very unusual person. He is an Indophile of a different variety. He loves Indian mathematics. Can you imagine? You must have found a lot many people loving Indian Vedanta, Indian philosophy, the Vedas, the spirituality, the works. Here's a man who loves Indian mathematics. And not just loves, he is actually in the missionary mode. He runs petitions and he runs campaigns on Twitter, and he's been requesting the Indian government. Some of us also have been, but he is by far the most strident, the loudest, and probably the most passionate about it. So, hello, Jonathan. How are you doing?
I'm very well, thank you, Sanjay, and namaste to all of your viewers in India. I would like to point out that whilst we look side by side on your computer screen and on the video, we are actually sitting at right angles to each other. So we're sitting like that. You're sitting straight up and I'm sitting out on planet Earth, out at the side. So it's one of the things to bear in mind. If we're thinking of Indian astronomers, they would have been very aware of such things that we seem to miss in our perception of the world. And that is that you and I, our bodies are pointed in totally different directions.
You see, we have a very, very lay audience. So you have to make things simple for them. That is one.
Yes.
And as you've been rightly saying, most of my audience would actually be scared of mathematics. So you have to tell them how to make it simple. And before that, the first question that I'm going to ask you, what has made you go on this mission?
Well, Sanjay, that's a very good question. It really started when I was in class 2 in 1968, when I had an argument with my teacher about her explanation of multiplication. I had picked up that India's 0 was missing from my teacher's explanation, and the explanation that my teacher was giving me in class 2 was based on Euclid's definition of multiplication, which predates India's invention of 0 as a number. And my school teacher and countless generations of maths teachers before her had only ever been taught ideas about Western mathematics. And perhaps because I was confused at the age of 7, I just couldn't believe my eyes at what I was being told about mathematics. And as it happens, I was right, and for centuries people had been wrong. I wrote a paper about it, but really for most of my childhood, I thought I was pretty stupid, because I found it difficult to understand how all the different parts of mathematics actually fitted together to make what many people call common sense. It's very often that people are taught mathematics through laws and rules, and they have to memorize information, and there's no simple intuitive understanding. And what happened was, 1983, I smashed my spine, and I was told if I moved, I might never walk again. And so I needed a miracle, and I wasn't sure how to pray, but I prayed in the intensive care ward of a hospital. And the prayer that I made was, "Dear God, if I can walk again, I will fix mathematics." So I know that that's not how you're meant to pray, but in that case, that's what I pledged, that if I could walk again and have children, I would dedicate my life to fixing mathematics. And so even though that my spine had been crushed, I was able to regain my health and walk again, and I've got 3 happy and healthy children. And so from March 1983, I have been living up to my promise that I made in hospital to fix the foundations of mathematics. So that's what I started off with, that goal. I thought I wouldn't really achieve anything, but a promise is a promise. And it became my my mission that the more I learned about mathematics, I just felt getting more and more confused until really I came across the mathematics of India, and then things all started to make intuitive common sense to me. But it was still very different to the laws and rules that I had been taught at school, and they have been taught all around the world to this day.
That's a wonderful mission and very well explained. However, you mentioned Euclid. I guess you must have met Dr. Raju, and Dr. Raju's Euclid challenge still stands. So that's something that you can take on.
I'm very aware that the tradition of the West is to portray a lot of black mathematicians as white, and there's a strong possibility that Euclid may have been dark-skinned complexion and possibly even a female. We don't have any real evidence of the actual proof of an individual called Euclid. In fact, many people mixed up Euclid of Alexandria with Euclid of Megara. So many of the early editions of Euclid's Elements were actually being credited to Euclid of Megara, who is a philosopher and not even a mathematician. So whether or not there is an individual called Euclid, the mathematics that is known as Euclidean mathematics was really essentially geometry. And that really led to the problem, because for the most of the last 2,000 years, mathematics in the West has almost been synonymous with Euclidean mathematics.
And in you at this point, we have had what is called the Shulba Sutras, and we know the Bodhayan Shulba Sutras, they probably predate the Euclidean geometry. And you yourself mentioned in your works about the Shulba Sutras. So would you like to discuss the Shulba Sutras vis-a-vis the Euclidean geometry?
Well, I think that one of the things that is important to get right is the order of priority in the history of mathematics. There's a saying that history is written by the victors, and in our case, it's usually the West who's written the history of the East, rather than the people from the East writing their own history. But what we know is that the idea of Pythagoras has got a very, very long history. And in fact, the idea of the Pythagorean triple, which is a triangle with the two sides, the squares on that right angle, the two smaller sides, the squares on those triangles' sides, sum to the area on the hypotenuse. What I can do is I can show a picture to your viewers that might make what I'm about to say a little simpler to imagine. So if I just bring this up onto my screen, you're now looking at a triangle. And if you look across the base of the triangle, you can see that it's 3 units long along the base. And if you look vertically, you can see that there are 4 units along the height, and on the hypotenuse, the long side, you can see that that length is 5 units. Now, this particular tool was very common in ancient Egypt as well as in India, and it was not so much a mathematical tool as a tool for construction. So we think about the pyramids, for example. They would have been built with these sorts of rope devices in the ratio of 3 along the bottom and 4 on the shorter sides, and then 5 on the hypotenuse, because that forces that triangle to have a right angle. So by having this tool, which is just simply a length of rope with 12 equal spaces on it, if you pull the rope tight in that way, you will always have a right angle, and therefore with a plumb line, you will always be able to have walls and the sides of buildings perfectly upright at an angle of 90 degrees. So this concept of a squared plus b squared equals c squared is a mathematical situation based on numbers to produce a right angle for construction. Okay, now what that goes back to 2,500 years ago in Egypt, and even 2,500 BCE in Egypt. And we also find, though, that in India, they changed this to talk about the squares on the side of those triangles. So there were the ratios of the numbers, which were known in Egypt in 2,500 BCE, and also in Mesopotamia by the Babylonians about 1800 BCE. But that didn't talk about the areas on the sides of those triangles. That was just to force an upright 90-degree angle for construction. It was India in the Shilpa Sutras who was the first to actually document the theory that the squares on the 2 smaller sides of a right-angled triangle sum to the area of the square on the hypotenuse. So it's really not a Pythagorean theorem. It's actually a theorem that rightfully belongs to India, because they were the first to talk about the theorem of the square on the sides of the shorter side summing to the square on the longer side. So that was around about 800 BCE that we know for a fact that that was documented. And then supposedly maybe about 200 years later, the Pythagoreans also had that formula as well. And it's just unfortunate that the tradition of the West is to always look towards Western sources, and very often the Greeks, for their history, and they really weren't aware of the fact that it was in the Shilpa Sutras. So I'll just stop sharing that image for a moment and come back to camera. And later on, there was a proof given by the Chinese. But the first actual stating of the theorem of a squared plus b squared equals c squared, the geometric idea, is definitely a first for India. And one of the things I think is really important is we saw that that tool that I showed was made from rope. One of the things about rope is it's a very powerful mathematical tool because it allows us to measure curves. Okay, now the Greeks, their tools were the compass for drawing circles and a straight edge. But the Egyptians and the Indians, their tool for creating circles and for measurement was rope. Now, as an example, you have a device around your waist called a belt, which measures the distance around your waist. You can't do that measurement around your waist with a Western straight edge.
Yes.
But your belt is like a rope that measures your waist, and so you can convert a curve, the length of curve, into a known measure using a rope. So the Shulba Sutras actually means the rules of rope. And we can do amazing things in schools and in classes, including things like squaring the circle, if we go back to the tools of ancient India and start to use rope and some of the traditional approaches of the East, rather than follow the West like slaves.
Well, I did host Dr. C.K. Raju, and he has what he calls Rajju Ganit. Rajju Ganit translated literally as rope mathematics. And
Yes.
he took a session with the Mathematics Association of Jaipur, Jaipur Mathematics Association, and he taught them the Rajju Ganit. And of course, now there's some movement to take it forward. But I think this Rajju Ganit or the rope mathematics, that's an idea that could really excite the youngsters, and that could make the teaching of geometry so much easier.
It's a fun activity. If you can get children to start having fun with their mathematics, it's really, they become little problem solvers, they become engineers. They start to look at the height of a tree, for example, and with things like similar triangles, they can work out the height of a tree or a street lamp via shadows. And all of these techniques involving measurements of shadows was what all of the ancient Indian mathematics was all about, because it was created by astronomers. And the shadows are always cast by the sun. So whenever you have the sun in the sky and you have shadows and you have the heights of devices from a horizontal ground that create the shadows, you're starting to create wonderful geometry. And look, the earth that we're on is round. So if we can start to really enjoy the mathematics of the universe around us, we actually find it's much more intuitive than we would expect. And there's a lot of common sense in India's mathematics that the West really forced us not to consider because of the role of the Western churches. That might be another question for later on.
Oh yes, definitely. The factor, the church factor is very important, because the church has interfered in many knowledge traditions in similar manner. But now the next question, the next logical question would be, coming from geometry and moving on to arithmetic and algebra, we find that the Indian astronomers, the Indian mathematicians, they had started using algorithms a long time back. Whereas right till the end of the first millennium in the Common Era, the West was still using abacus and the Roman numerals. In fact, Roman numerals have gone on till about 15th, 16th centuries. And they were not able to really use zero in the way that probably even the Arabs used. So I just want to get your idea about the use of algorithms, and then on to your real passion, the zero.
Well, I'll just explain to you and your viewers, Sanjay, what my idea of mathematics is about. Because there's a lot of philosophy in mathematics that gets in the way of understanding of how simple mathematics really is. The way that I approach mathematics is, I say that mathematics is all about relationships between quantities, okay? So when we're trying to explain the universe, everything in the universe has some measure or count of a quantity. Now, if we go to modern physics, we know that there's fundamentally energy and matter in the universe. Now, with numbers simply count or measure quantities. And it is impossible to have any quantity that is less than zero. And yet, the idea of the West is that negative numbers are less than positive numbers. Whereas what we really should be teaching children is that negatives and positives are equal and opposite, like two people balancing on a seesaw. Or in America, they might call it a teeter-totter. But if you've got two people and they're balanced on a seesaw, the force pushing down on this side equals the force, the oppositional force pushing down on this side. You have a force going up that way, you have a force going up that way, and all the forces are balanced and the forces are equal and opposite. Yet the West introduced the idea, because they didn't understand Brahmagupta's mathematics, that negative numbers are less than zero. Now, numbers, again, remember, numbers simply count or measure quantities, even if those quantities are abstract units. So we introduce negative numbers as representing quantities that are less than zero, and that's impossible in our known universe. We've got ideas like Newton's third law. For every action, there's an equal and opposite reaction. And yet, all of the laws of modern physics agree with the mathematics of ancient India, but the Western maths that we're taught has many illogical ideas that just are absurd, and yet we're taught that that is science, and it's not. It's a lot of nonsense that needs to be dismantled step by step and replaced with a simple sequence of known empirical, logical connections in relationships between quantities. So if I give you a very quick example, I drove here in my car. I had a quantity of distance and I had a quantity of time.
I'm having a little problem with your signal. Your voice is breaking.
Can you hear me now?
Yes.
Okay. The point I'm making is that all quantities are greater than zero. And you cannot have any quantity that is less than zero. And for us to talk about negative numbers as being less than zero is physically impossible when numbers represent counts or measures of quantities. The other thing that numbers also can do is they can count actions as well. They can count change. And you cannot have any counts of change that are less than zero either. So we've got all of these ideas that arose in Western mathematics that are just called absurd. They're called irrational. They're called all of these ideas. We use them, we teach them. But if we start to step back and look at some very simple physical models that we can use with children, all of a sudden things start to make sense. And young children have no problems learning mathematics really quickly, very, very rapidly, with total understanding if we give them correct information. But when we give them incorrect information, the brains of those children, which are the most remarkable computer on the planet, the human brain, the brains of the children learn super rapidly when there's correct input into those brains. But if we put the wrong ideas into the human brain, people will reject those ideas. And I rejected those ideas at school. And I ended up doing quite okay at mathematics, but I struggled with mathematics for a very long time. And the reason was I was thinking too much. My teacher in class 11 told me, Jonathan, don't worry about mathematics. It's only confusing if you think about it. Okay. So my mathematics teacher was telling me, don't think about mathematics, Jonathan, because you get confused. But I had always been trying to understand mathematics, and that's what I've been doing for the best part of 50 years of my life. Since that argument with my teacher in class 2, I've been just trying to understand the basic building blocks of how mathematics works. And I've looked at mathematics in a lot of different cultures, but really it starts in the 7th century, as far as I'm concerned, with the writings of India's Brahmagupta. And so what I do is all of my lessons that I create for children, which are very enjoyable, they're cartoons, they're colour, they're fun, there are games, there are songs, they're all based from my analysis and interpretation of the Sanskrit of Brahmagupta and Bhaskara and Aryabhata and so on. So I've gone back to the men who built mathematics the first time around when it was correct, and I've then developed it with ideas based on modern physics and also how the child's brain wants to learn. So a lot of the children, they play, they see colours, they have games, and they are learning about relationships between quantities, and that is the mathematical understanding that's been missing for the best part of 1,200 years, since India's mathematics seemed to have been lost around about 1,200 years ago in the early part of the 9th century in the Arabic world.
Can I interrupt you on this point? Because you also mentioned that the 0 was actually transmitted to Europe through Arabia. And you mentioned in your writings that even the Arabs did not understand 0 properly. So could you just explain that a little bit more for the benefit of our audience?
Yes, okay. The Arabs, they loved the Hindu base 10 system of numbers. And I'll give you a very simple reason why. I'll just write on a piece of paper. I'll write a couple of numbers. Now, as you may know, the Arabic read the other way to us. We read in one direction and the Arabic world reads in another. So if you're an Arabic person, the Roman numerals present a great problem, because is that number a 6 or is that number a 4? So when the Arabic world was approached with Roman numerals, which you must remember the Roman Empire was very dominant for a very long time. Roman numerals were basically everywhere in the world that modern science was around. So you had confusion in the use of symbols for numbers. So when the Indians came along, they had this wonderful invention where instead of having those sorts of symbols, they would have symbols. Now, I'm not sure if that's the right way around. It might need to be reversed. I wonder if I can reverse that. But you get the point that 6 and 4, they stay the same numbers no matter which way you read those numbers. Right. But the Roman numerals change the number according to which way you read that number. So the Arabs were very interested in the Indian base 10 system of numeration. And they really were only interested in one chapter of Brahmagupta's work, and that was chapter 12 on basic arithmetic. That seems to have gone across to the Arabic world. So they knew how to do addition, subtraction, multiplication, and division with the standard types of algorithms that India had developed. But what they did not understand is, and the 0 too, by the way, was just simply a way, if we had the number 107, if you didn't have the 0 in the middle, it might be taken as being 17. So they saw that the 0 was a way of pushing the digits apart so the digits would be in the correct place value, so they'd be able to read those numbers. So the 0 that came to the Arabic world was almost like a punctuation mark. It was like a dash. It was like a separator that forced the digits into the correct column. But the Arabic world didn't really understand that India's 0 was defined by Brahmagupta in his Sankalana rules as the sum of two equal and opposite quantities. So Brahmagupta would say -4 and +4 is 0. And he wouldn't say that -4 is less than +4. They're simply equal and opposite. So today, if we had gravitational force off to that direction of a certain number of newtons, and we had another gravitational force off to that direction of an equal and opposite number of newtons, my head will stay still because the forces are equal and opposite and they balance each other out. And there's 0 net force, so I remain stationary between those two forces with their gravitational pull. The Arabs were very much interested in, I would say, the commerce. The Arabs were great traders, and Muhammad was a trader and a merchant. So the Arabs were very much using the Indian mathematics, particularly for things like laws of inheritances and financial transactions and so on. And that came out of chapter 12 of Brahmagupta's Brahmaspita Siddhant. But the really wonderful stuff was in the algebra of Brahmagupta. That was chapter 18. And I suspect that perhaps chapter 18 of Brahmagupta's fabulous work didn't really travel to the Arabic world. The simple arithmetic did, where 0 spread out the digits, but there were no negative numbers in any Arabic arithmetic or algebra. There never was, and there never was any understanding of 0 being the midpoint between negatives and positives. 0 was a state of balance. It was not just the absence of quantity, it was also when two opposing forces or quantities balanced each other out. So the 0 was misunderstood for its full power. So there are many what I call laws of Brahmagupta. I've kind of documented 18 laws of Brahmagupta that involve addition, subtraction, multiplication and division on positives, negatives and 0. And most of those laws are totally missing in the Arabic world because they had no concept of 1 as a number, let alone 0. They had no negative numbers either. So the algebra that then developed was 200 years after the algebra of Brahmagupta. The algebra of Brahmagupta was symbolic and it used 0, and it often led to ideas of negative as well as positive solutions. But the algebra of the Arabic world was only based on positive rational numbers. They never had an equation equaling to 0, for example. And the metaphor that I think was in the minds of the Arabic mathematicians is, I suspect that because they were merchants, they had a kind of like a pan balance way of balancing equations. So the Arabics wrote about balancing equations and what you have to do to make sure that the equation's balanced. So how could you have a whole lot of mathematical terms on this side that would balance to 0? The scales would never balance if you had a whole lot of terms on this side and you had 0 on this side. So I think that there are these kind of conceptual blocks that meant that they never truly understood the empirical mathematics of India that was created by astronomers who were scientists. They were looking at the universe and they were creating mathematics that matched their observations about relationships between quantities. So Indian mathematics came from observing the universe. It didn't come from philosophy of Aristotle or Plato. It didn't come from rules from the church about zero is the realm of the devil and only God is infinite. So ideas of infinite and zero, which were popular in the East, they were taboo in the West because the church shut down those ideas as they were seeking to colonize the East and increase their power and wealth at the extent of the local culture and science. So forgive me for talking so much, but I am obviously very passionate about where mathematics went wrong.
I'll ask you one last question, because we are already above our time quota.
Okay.
This question about empirical mathematics and what is also called the inductive method of India and the deductive method of the West. And we have this strange situation when you try and prove 2 plus 2 equal to 4 using the deductive methods, as was done, I think, in the Principia Mathematica by Russell and his friend. It takes something like 278 pages.
I've got something here to show you as the power of empirical observation. Just imagine that we've got positives.
I'm losing your voice again.
My apologies. Imagine, can you see that okay?
Yes.
Okay. Imagine that these red dots are positive, and imagine that these black dots are negative. Okay? You've got 3 red and you've got 2 red. So the 3 are greater than the 2, very obviously. Here we've got 4 negatives and we've got 3 negatives. And so if we look at our eyes will tell us that 4 negatives are greater than 3 negatives. And yet what do we teach our children? We teach our children that -3 is greater than -4. But that's empirical. Look, you have to believe your eyes. Now, what you're doing here is you're looking at with your eyes and you're seeing that 4 negatives are greater in number than 3 negatives. So we must fix our integer ordering. So -4 is greater than -3. Now, the laws of Brahmagupta agree with this very simple idea. And the laws of physics agree with this very simple idea. But we've had such nonsense evolution of mathematics because it was based on ancient Greek mathematics without 0 or negative numbers or even 1 as a number. We haven't yet ever really understood elementary primary school mathematics. So that's why I'm passionate. I found problems when I was in class 2. I made it my life goal to fix the mathematics of primary school children. And that's why I'm talking to you today, to say that mathematics is now simpler and more powerful than it ever has been. And I'm just wanting to share all of my research with Narendra Modi, with any teacher in India, with any child in India. I'm writing a series of ebooks, and those ebooks on mathematics, which I call Podometic, I'm giving those away free of charge to everyone in India so they can at last begin to understand the magnificent mathematical heritage of India that has been missing for well over 1,000 years.
That's a wonderful explanation, Jonathan. And I would urge any budding mathematician in the audience, or even a student. I know a lot of students who appear for competitive exams and who find understanding mathematics very difficult. So all they do is to cram up the laws of mathematics and then try and navigate this minefield. Please listen to this lecture very carefully, and if you want some help, certainly we are here to help you. Our mission is to make understanding of mathematics easy and make understanding of mathematics accessible to everyone. Thank you so much, Jonathan, for coming to this Jaipur Dialogues. And this is your debut on Jaipur Dialogues. And I'm sure that we are going to have many more such productive sessions. Wonderful to have you. Thank you very much.
Thank you.
Press the bell icon on YouTube and don't miss another update.